I'm making an NES emulator, and I have 28 days left to finish it by Hedgehog Day. Mary and her husband Joseph were in Bethlehem doing their taxes. They came back to their home in Nazareth with a baby boy. 2 years later, King Herod sent 3 wise guys to kidnap the child. They brought gifts to Joseph and Mary to distract them. Some congregations celebrate this as Epiphany, or Three Kings Day. So anyway, neither Meson nor FCEUX was emulating an MMC1 edge case where the PPU reads video memory and causes it to switch program banks. I plan to write a new test ROM just for this behavior. At the moment, I felt it more pressing to improve debug logging and added some of the sound chips registers. I was about to sort the instructions into groups again. I knew from yesterday's 12 lost minutes that I'd need to test often. So I built the nest test front end again and ran it as my baseline. The stop opcodes don't behave quite the same as in hardware. This is on purpose. I left a hook open to let a front end repurpose these instructions, such as to let a game control the high-level emulation. This approach is sort of like the cop instruction on 65816. Checking my work in nest test about once a minute, I opened a second editor to use as a bigger clipboard. Check, 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 check. That was all of them. I ran Blarg's test again, and it was still fine. The nest test log disassembles the instruction at the program counter. This uses what I'll call a peek function, a way to read memory without actually clocking the rest of the system. I moved work RAM, SRAM, and ROM reads to a peek function. Peeking doesn't really make sense for PPU and sound registers. Those change constantly and many have side effects when read. I documented the relationship between peek and read. When I document C functions, I use a style inspired by Java. Before each function is a block comment beginning with 2 asterisks, then an explanation of what the function does, then its parameters and what it returns. JavaDoc uses a sentence fragment in third-person singular. This agrees with it, such as reads or draws. Python has a different convention for its doc strings. They go inside the function and start with an imperative like draw. I wanted to know what verb form command line users expect when they give the help option. I could use peek to disassemble each instruction before it runs. I took NestDev's opcode matrix and turned it into a lookup table. I did this with find and replace because I don't really know sed. I almost just lost data. I was replacing shorthand addressing mode notation for the lookup table. I mistakenly had mousepads set to replace in all open documents. Usually I've used all documents mode for refactoring, but the shorthand for immediate addressing mode happened to match the start of an include statement in C. Fortunately, I caught it and reran Blarg's instruction test. I closed the other files while making this lookup table. Reformatted it with 16 instructions per line of C code. I defined a struct to hold each instruction and a set of codes for addressing modes. I made a table of the expected length in bytes for each mode, a set of format strings, one for each mode. I just saved it with the wrong extension. That's why the syntax wasn't highlighting. I'm way too assembly-brained from my other job. C's string handling encourages fixed-length buffers. I chose a size that I thought was long enough for one instruction. I renamed the file to indicate that it was actually in C, and highlighting was back. Showing my work for a choice of buffer size, I started writing a disassembler that reads these tables. And it was a double header. C also encourages fixed-size input buffers. No 6502 instruction is longer than 3 bytes. Recent C lets functions take array arguments with size marked static. This documents an assumption that the array is not a null pointer and has at least some minimum size. Each disassembled instruction starts with a 3-letter mnemonic. If there's no operand, terminate the string with a 0 byte. Otherwise, leave a space and follow the format string. A placeholder in the format string means insert the operand bytes. I considered it more readable to write operands less than 10 as decimal and larger operands in hexadecimal. I distinguished small absolute operands from zero-page operands the same way as the CA65 assembler. Add A, then a colon. I calculated the branch target address by adding the program counter value. I made a mistake in the value comparison. I added a disassembly to the nest test frontend's register log. Fields in a printf format string with the width are aligned on the right. A leading minus sign overrides it with left alignment. I made the disassembler compile. I read the 3 bytes of the program counter in peak mode to pass them to the disassembler. This meant giving the disassembler its own header file. It almost compiled. That looked like an instruction. I did the same to the headless front end. It was disassembling a ROM startup code, but there was still a mistake. I cut down the log to fit on an 80-column line. With 10 minutes left, I decided to start on sound, or at least the status register of the audio processing unit, or APU. The APU has its own timer independent of the PPU. It acts as a time base for decay, pitch sweep, and note length effects. I started to add APU registers to the machine state. I checked what happens at power up and on pressing the reset button. I chose to do the sample channel first because games rely on its timing, such as Firehawk and Time Lord. Yesterday I wrote a disassembler to help me understand trace logs. It wasn't perfect. I plan to address that. The short option -F for maximum frames wasn't working. Fixed. One instruction made the disassembler overflow the output buffer. I had swapped the small and large hex constant cases. Fixed. I checked how another emulator distinguishes small absolute operands from zero-page operands. That emulator works the same as Apple II's mini assembler, printing more leading zeros for a small absolute operand. I'll stick with CA65's method because it's what I'm used to. GNU Core Utils provides many basic commands on most Linux systems, things like ls, cp, chmod, echo, tail, sort, test, date, and nice. Their help text ends with a URL to report bugs. I added the URL of family size VM's topic on NestDev to the help text of both front ends. I also noticed that Core Utils help text uses the imperative. I followed that for consistency and made the front end's names consistent in error messages. They both look good to me. On to sound. The APU frame counter is an internal time base derived by dividing the CPU clock. One thing it controls is note length. The program can tell when a note has ended by reading a register. Some CPU tests measure how fast an instruction executes by playing a note and running an instruction until it finishes. That's why emulators need a frame counter even before sound. I took a lot of notes because this was unfamiliar to me. I hadn't really used the frame counter while developing games. I began translating some of my notes to C. Remember tick APU from a few days ago? It was about to get bigger. A lot bigger. The frame counter clocks the envelopes about 240 times a second. It clocks the sweep units and note lengths at half that rate. I put in placeholders for what to do when those happen. The APU can assert an interrupt 60 times a second. Only about 2 games actually use this. It's been speculated that the interrupt was meant for devices using a 2A03 CPU without a PPU in case the Famicom didn't sell well. For most games, it's just something to turn off at startup. I made sure the frame counter was ticking at the right speed. That looked close enough. I hooked it up to MMIO registers. The APU can make 2 kinds of interrupts, one when the frame counter ticks and one when the sample ends. They're both acknowledged through hex 4015, one through reading and the other writing. Reading that same register tells which notes haven't ended yet. I added names for the relevant status bits. The frame counter is nowhere near done. I forgot to update the day of the week on my whiteboard. Back to work on the APU frame counter. Like the mapper, the frame counter can interrupt the CPU. I combined the mapper and sound IRQs into one line that the CPU sees. I made it compile. And AccuracyCoin still gray-screened. I added logging when acknowledging APU interrupts. That didn't help. I added even more logging and refactored acknowledging the interrupt into its own function. Still didn't help. I shifted gears to Blarg's branch timing test. Fortunately, this test had source code available, although somewhat heavy on the macros. I'd need to time the beginning and end of a note first. I looked up what it'd take to play sound in SDL2, and the first step was to initialize SDL2's audio subsystem. I took an opportunity to clarify some variable names before reading how to open a sound playback device. I remembered from Python's Wave module that in some cases, big-endian processors like the PowerPC and a Wii need byte swapping. I checked whether that might affect me and continued writing a first draft. An audio output stream was something else to free at the end. I made my draft compile. Once I added sound, I needed everything to run in real time. Logging can take quite a chunk out of that. I looked up how to stuff audio into an output stream. Out came the calculator to find a convenient sample rate. I prefer to work in rational numbers or exact fractions. That lets me use Bressingham's algorithm to avoid rounding error. Once in real time, I needed to read how much sound was already in the queue to control my frame rate. I had an output channel. I wasn't putting anything into it. I did the Bressingham thing, filling X many output samples per Y cycles. I had to copy the loop twice because of how this front end waits for VBlank. I looked up how to call the function to send samples. Until I had something emulated, I had it generate a sawtooth wave. Another double header. I shouldn't make a habit of this. I added logging to see how many samples I was sending and how many samples it was receiving. You can't hear it here, but it still wasn't sounding right. I tweaked the formula for the sawtooth wave. Oh shoot, I missed this. I was supposed to send a byte count. That means send twice as many as the number of samples. Then I had to change how the frame rate works. The emulator wasn't keeping up with real time. I turned off the sanitizer and turned on the optimizer. That still wasn't enough. Back to the SDL manual. Was the output format getting changed? I changed output queue measurement to also count bytes. I crunched the rational numbers for a couple other output rates. The output loop was where I wanted it for the moment. I continued toward figuring out what to return in hex 4015. AccuracyCoin was still grayscreening and reading 0 from hex 4015. I collected a log to see what it was doing with the value around where it turns rendering off and on. I confirmed my guesses in the source code. I got to the part where AccuracyCoin tests for sample playback. It took me back into the part that writes text to video memory. I saw exactly where it printed text in the good emulator. I cross-referenced that in the log of my emulator. It was trying to write the letters CPU to the name table, which I could see in a name table dump. This name table dump was even more complete, but still a blank screen. I logged select PPU registers at the end of tracing. I needed to find why it was building a menu but not rendering it. I logged the palette and it didn't look solid like I had suspected. It wasn't sound at all. It was the left side clipping bit. Instead of only clipping the left 8 pixels of the background, it was clipping the whole thing. Facepalm! I needed to search the internet for examples of SDL2 audio output. It took me almost 2 hours to catch the wrong day name. I needed a mental health break.